let's take a look at our second example. And again, we are going to go through those 4 steps. So let's start with step 1. Step 1 is analyzing the function itself by looking at domain, and then x-y-intercept, and vertical horizontal asymptote. So part A, let's begin with our domain. And this, you can think of it as e to the negative 3x squared or 1 over e to the 3x squared. Either one is fine. Now domain here, we do not have to worry about any x value. It will not make 0 because think about this. If you plug it in and then do a 0, if x equals 0, then you have e to the 0, and anything to the 0 power is 1. So our domain is all real numbers. So all real numbers. So negative infinity to positive infinity. Let's find out the x-intercept. X-intercept is when the y equals 0 and we solve for x. So we are gonna have 0 is equal to 1 over e to the 3x squared. And same thing as domain, the only time, so the only way the fraction is equal to 0 is when the numerator equals 0 and numerator is 1. And so I'm never going to have a 0. So we have no x-intercept. Okay. Let's also, and then no x-intercept. Y-intercept is the opposite. We set x equals 0 and solve for y. So we plug it in. E to the negative 3 times 0 squared, which is equal to e to the 0, which is equal to 1. So we do have a y-intercept. Y-intercept point is 0, 1. Okay. All right, now let's find out the vertical asymptote. So we do not have a vertical asymptote because vertical asymptote is where domain is undefined, but it's defined everywhere. So we have no vertical asymptote. Vertical asymptote. What about horizontal asymptote? So horizontal asymptote is when the limit as x goes to infinity of 1 over e to the 3x squared. Now, if you plug it in really big number, I'm going to have 1 over really big number. So therefore, 1 over really big number really is a 0. We do have a horizontal asymptote that's at y equals 0. So step 1, finish. Step 2, let's take a look at our second derivative. So if I take the second derivative, this one, that's a chain rule. So I'm going to have e to the u times du. So that's going to be, let me erase it so I can see it clearly. I have e to the negative 3x squared. Derivative of our power is negative 6x. So in other words, it should be a single prime, not double prime. Will be negative 6x e to the negative 3x squared. So let's find the critical value. That will be either f single prime equals 0 or f single prime does not exist. So this will be equal to, in other words, negative 6x over e to the 3x squared. So the fraction is 0 when the numerator equals 0. So that means negative 6x squared x equal to 0. Fraction does not exist when the denominator equals 0. here I'm going to have negative 6 divided, so x equals 0. That's one possible critical value. And second one is, again, same issue here. We are never gonna have a x value where you plug it in, you're gonna get a 0, so we do not have a critical value coming from this. So let's create a number line. So create 0 here. This will be for f prime of x, region 1, region 2. Let's test it. Region 1, I have test number x equal to, let's pick negative 1. And then for second region, test number x equal to positive 1. I'm going to make a little bit small so I can squeeze in. And then step 2, let's also resize. Okay. So let's plug it in into our first derivative, f prime of negative 1, which is this part over here. So negative 6 times negative 1 over e to the 3 negative 1 square. That's a positive 6 e cubed. So I have in a decimal value about 0.299. So that's a positive. If I plug it in positive 1, I'm gonna have negative 6 times 1 all over e to the negative 3 1 square. So I have negative 0.299 using a calculator, so negative value. So that means I have increasing function and decreasing. And because we have sign change, this is a critical value that has increasing, decreasing, so that will be a local max. Okay, so let's write it out over here. So many of the things that we are doing is just a review from 4.1 and 4.2. We've been doing this number of times at this point. So we have a increasing on the interval negative infinity all the way up to 0, not included, and decreasing 0 to infinity. And then we have local maximum this time at x equal to 0. Okay, let's highlight that. Okay, and let's go to step 3, which is a second derivative. Okay, so for the second derivative, let's go back and then copy down our first derivative. This was our first derivative. Okay. And it's up to you. I'm just gonna use this on the product rule because I prefer product rule, but you can use quotient rule. So this is a product, two things being multiplied. So first one, negative 6x, and derivative of this term over here will be, using the chain rule and everything, I get negative 6x e to the negative 3x squared. And then we switch around, right? Derivative of this one is negative 6, and then this term remains the same, e to the negative 3x squared. Let's do some arrangement here. I have this 2 makes it positive 36x e to the negative 3x squared. This is minus 6e to the negative 3x squared. I noticed that they have a common factor, so factoring out 6e to the negative 3x squared, I'm going to have 6x I forgot, when I multiply x, I should have x squared. So 6x squared minus 1. That will be my second derivative. Now, let's find a inflection point so we can partition the number. So in this case, you can also rewrite this. I have a negative exponent, so I can have 6 times 6x squared minus 1 all over e raised to the 3x squared. So two possible way when second derivative is 0 or second derivative does not exist. So the only way the fraction is 0 is when the numerator is 0. And then here, same reason, I'm never gonna have this part equal to 0, so I don't have to consider anything solving for x in this case. Let's keep going. Divided by 6, so 6x squared minus 1 equal to 0. Add 1. I have 6x squared equal to 1. Divided by 6. Divided by 6. So x squared is 1 over 6. Square root, once you square root, you have two answers, plus or minus. What is a square root of 1 over 6? I'll just get a decimal. That will be 0.41 rounded to the 2 decimal place. 0.41 rounded to the 2 decimal place. So I have two critical value at negative 0.41 and then positive 0.41. So we have three regions to test value. 1, 2, 3. So for first region, I'm gonna use test number -1. And then for second region, I'm gonna use test number anything between negative 0.41, positive 0.41. Let me use a 0. I can use a 0 because it is I have no restriction because my domain is all real. And then for third one, let's use test number x equal positive 1. So let's plug it into our second derivative, which is right over here or here, either one. And I'll use a calculator to get all those numbers. So f double prime -1, I'm just gonna plug it into this function here. So I have 6e raised to -3 -1 square, 6 times -1 square minus 1, and then putting directly onto a calculator the whole thing, I got 1.49. So that is a positive here. Okay, let's use 0. So f double prime 0, that's 6e raised to -3, 0 square, 6 times 0 square minus 1. Again, putting into a calculator, I get exactly -6, negative value. Last one, f double prime equal f double prime of 1. So I have 6e raised to -3, 1 square, 6 times 1 square minus 1. Putting into a calculator, I get positive 1.49. So I get a positive number. That means I have a concave up, concave down, concave up. This part is my one of the inflection point. This also is my inflection point. Why? Because we have a sign change, positive to negative, negative to positive, positive to negative. So sign change, negative to positive. So we have two inflection points. Okay, so let's write it over here. We have concave up, two region right over here, right over here. So negative infinity to negative 0.41 union with positive 0.41 to infinity. Concave down, you have a concave down from negative 0.41 all the way up to 0.41. Okay. And then we have a two inflection points. Inflection points are occurring at x equal negative 0.41 and then positive 0.41. Okay. So I'm going to highlight these. Now, let's use all these information and then sketch the graph. So just like what I did, I'm going to copy all the information that I found to sketch my function. So let's copy the domain here. We have a domain defined. What else? And then we have a no x-intercept, y-intercept, here, no vertical asymptote, and then horizontal asymptote here. These are all the information that we have found. And then we know something about where it's increasing, decreasing, and we do have a local maximum this time. And then finally, concavity and inflection points. Okay. So let's create a quick grid. Let's indicate our intercept 0, 1, 0, 1 right over here. So I got that. And then we have a horizontal asymptote y equal 0. So that means right over here. That's a y equals 0, horizontal asymptote. We should partition our section. So no x-intercept, so nothing, no vertical asymptote, so I'm not going to draw anything. All real, so let's focus on this part here. We have kind of like, so 0 is an important point because that's a local maximum. And then we have these numbers that we need to partition. So if this is negative 1, negative 2, negative 3, and positive 1, positive 2, positive 3, negative 0.41 is kind of like over here. And then positive 41 is right over here. Now, for now, I'm not really drawing the vertical line because I'm going to erase in a minute, but I want to partition divided into 3 sections. Because remember, in this section, right over here, we have a concave up, and take a look at this all the way up to 0. We have an increasing, so this part which is region 1 right over here. That's a concave up and increasing. So concave up and increasing, concave up, increasing will be this part here. So I should have some kind of this picture in region 1. This part, 4.1 all the way up to infinity, I have a concave up, partially all the way up to 0. This tiny bit, it's a concave up with the increasing. This part over here is concave still up but decreasing. Okay. Let me also mark over here. This region was just very simple, concave up and then increasing, so it will be this picture. So concave up increasing will be still this one. Concave up decreasing will be this part here. So I should have this graph coming. Lastly, this region, I have, oh, my mistake. I misread it. 0.41 to infinity, that's this part here, concave. Let's do it again. My apology. Let me rewrite it again. Let me organize it better. I'm gonna partition into this 1, 2, because that point is important, 3, and then 4. So let's write it out. 1 is negative infinity to negative 0.41. In this particular region, we have concave up, and then all the way up to 0 is increasing, so concave up, and then increasing. Region 2 is negative 0.41 all the way up to 0. I even partition it further because there is a decreasing going. We have point all the way up to here, we have a concave up, but we do not have an increasing. We have a concave. We have a concave down, because 0.41, that's still 0.41, but then we have a decreasing all the way up to 0. So we have a concave down and then decreasing. Okay. Number 3, 0 to 0.41, we have concave down, and then it's past 0, so we have a decreasing, 0 to infinity. And finally, 0.41 to infinity, that's this part over here, concave up, and then decreasing. So how does it look like? If you have a concave up and then increasing, so this will be this part over here. So I have this picture in region 1. Concave down and then decreasing will be this part here, this part here. And then you have concave down and then decreasing, so concave down and then decreasing, so it will be this part. And then you have concave up and then decreasing, so it will be this part here. Okay, so let's start putting this into our graph. This is kind of like what's happening. Remember, these blue line is not a vertical asymptote. It's just for me to boundary. And then we kind of have concave down. And then decrease. Something is weird. Oh, I'm sorry. This is concave down and increasing. My bad. Why? Because it's all the way up to 0. All the way up to 0, it's increasing. So I should have concave down and increasing, so this part here. Okay, so I'm going to have kind of like continuing like this shape. So looks like I'm gonna have something like this. And then I know I have to go through this point, so it's kind of like this and this. Kind of sharp turn. Okay. Here, I have concave down, so I'm going to indicate this, and I know I have to go through this point here, and then continuing this shape, and then I cannot go past y equals 0, so it looks like I'm gonna have like towards this one. So I kind of have a curve that looks kind of like this, going through 0, 1. Okay. Whew. So that was a long problem. You see that I kept in track and then partition it further, even if I have all this information, because it gets tricky. So do much as partition as possible to get an accurate graph. Okay. And then next part, we will look at our homework problem.